This is the Chem 1 lesson over Introduction to Stoichiometry. So stoichiometry is a really big word that represents something pretty simple, and it's studying the amounts of things and comparing moles within chemical reactions. So basically that means we're going to take mole calculations, which you guys learned about in December, where you learned how to do all kinds of calculations using the molar mass to find the number of moles, or going from moles to liters of a gas at STP, or even calculating how many particles there would be in something. And you use the mole map, right? Those three conversions fit in there. You're able to convert between all of them for one substance. And next, you learned about chemical reactions. You learned about 5 different types and how different elements and compounds can come together in different combinations to form new compounds and elements. Now we're going to put those two things together. So we're going to take amounts, right, and mole calculations, and we're going to combine it with chemical reactions. So now we're not going to be just doing calculations with one chemical, but we're actually going to change chemicals within a chemical reaction. So it's smushing them together. And stoichiometry really just means it's the study of the amounts of things consumed or produced in a chemical reactions. So in order to be able to do stoichiometry, you have to start with a balanced equation. So if you look here, we have a synthesis reaction between aluminum and oxygen. It's not balanced, so the first thing you're going to want to do is balance it. So we're going to need to get 6 oxygens on both sides and 4 aluminums on both sides. And those coefficients, those big red numbers I put in there, serve as a ratio of reactants and products. So for every 4 atoms of aluminum, I'm going to create 2 formula units, or 2 molecules of aluminum oxide. So my ratio here is 4 to 2. But atoms are really small, so it's not really very realistic for us to talk about 4 atoms of anything. That's way too little. What we should think about is that for every 4 moles of aluminum, we create 2 moles of aluminum oxide. So these coefficients can be ratios for single elements or molecules, but more realistically, we should be using moles. So to learn stoichiometry, let's just start with something really simple, making a peanut butter and jelly sandwich. Let's say you make it by using 2 slices of bread, a tablespoon of peanut butter, 3 teaspoons of jelly, put those together, and you're going to get a peanut butter and jelly sandwich. So how many teaspoons of jelly would be required to use 36 slices of bread? So this is basically saying, okay, I have 36 slices of bread. How many teaspoons of jelly would I need? So we're going to use dimensional analysis, right? Think about our mole calculations. We have 36 slices of bread, and we need to convert that to jelly. So I'm going to have to cancel out my slices of bread and convert it to jelly. And do we have a ratio between slices of bread and jelly? We do. I know for every 2 slices of bread, it requires 3 teaspoons of jelly. Excuse me, this should be teaspoons. So now we would take 36 times 3 divided by 2, and you're going to get 54 teaspoons of jelly. So our conversion factor came from the coefficients in our balanced equation. So in order to be able to do this, we always have to have a balanced equation. That's going to be that ratio. But we're not going to be dealing with bread and teaspoons of jelly. It's going to be with moles of different substances. So in example number 1, how many moles of ammonia are produced? So maybe you want to write underneath that question mark, moles. When we start out with 0.6 moles of nitrogen, reacts with hydrogen. So I've kind of written out what was given, what I'm trying to get to in the problem. We're given that we're starting out with 0.6 moles of nitrogen, and we need to convert that to moles of ammonia. Conveniently enough, we have a balanced chemical equation, and I can see my ratio is, there's really an imaginary 1 there, for every 1 mole of nitrogen, I can create 2 moles of ammonia. So that's where that mole ratio comes from. So what we've done is that mole ratio, that idea of 1 to 2, is our mole ratio in the equation where we're able to actually change substance. So this is where it does become very important that you write what chemical you're talking about. Because if we had just put 1 mole on the bottom and 2 moles on top, we wouldn't know what. That's not a conversion, right? 1 mole is not equal to 2 moles. In this case, with this chemical reaction, 1 mole of nitrogen is equal to 2 moles of ammonia. So you do have to now put the substance in there. If you don't, it's not going to be clear what you're converting. So our answer to 3 sig figs would be 1.20 moles of ammonia. So our next problem, we know we got the formation. So our next example, we're given an equation. It's not quite balanced yet, so we're going to need to do that. So let's see, we're going to want to make 6 oxygens. So I would put a 3 here and a 2 here. It gives me 4 aluminums. Now I have my balanced equation. There we go. And let's read the problem. Let's check it out. So let's see, formation of aluminum oxide from the elements aluminum and oxygen. Great, synthesis reaction. How many moles of aluminum are needed? Okay, so question mark moles underneath aluminum to form 2.3 moles of aluminum oxide. So in this case, we're given the moles of our product and we're asked how many moles of a reactant. And that doesn't matter. We can convert reactant to product, product to reactant. We can even convert from reactant to reactant here if we were asked. Any combination as long as we have that mole ratio. So I'm going to start with my given, 2.3 moles of aluminum oxide. And now I'm going to have to cancel out my moles of aluminum oxide. And I need to convert it to moles of aluminum. Check out our mole ratio here. For every 4 moles of aluminum, I can create 2 moles of aluminum oxide. So that is going to be our relationship there. Now that we have that and we've canceled out our moles of aluminum oxide, converted it to moles of aluminum, we've done. We just have to do the math, multiply and divide. Round the answer to 2 sig figs, you're going to get 4.6 moles of aluminum. Our third example is a little bit different. We don't have a balanced chemical equation here, so we're going to have to write one. So we're going to have to look to see kind of what's given to us in the problem. We're asked how many moles of copper are produced. So that tells me that over here on the product side, I'm going to have copper. And we're told that 1.75 moles of copper 2 sulfate react. So over here, I know I'm going to have copper 2 sulfate, Cu plus 2. SO4 is negative 2, so a 1-to-1 ratio. And it's reacting with iron metal, so it's just iron. Single replacement reaction. So you could double check on your activity series that this reacts. We're told in the problem that it is, but in fact iron is more reactive than copper, so this reaction can happen. So that means we're going to end up with a compound between iron and sulfate. So since we don't know the charge on iron, we're going to have to make that assumption. So if you look at your back periodic table, figure out which charge for iron is circled, it's plus 3. So we're going to end up with Fe2SO4 3. Don't forget, we are going to need to be sure we have a balanced equation. So I'd probably start by balancing my irons with a 2 and my sulfates with a 3, which means I'm going to have a 3 in front of each of my coppers. Now that we have a balanced chemical equation, we can now write out what's given to us in the problem. We're starting out with 1.75 moles of copper 2 sulfate, and we're asked for how many moles of copper are produced. So we can start with our given here. 1.75 moles of CuSO4. And so that means we're going to have to cancel out our moles of CuSO4 and convert it to moles of copper. This is a matter of our mole ratio, so let's go up here and check. For every 3 moles of copper 2 sulfate, I get 3 moles of copper. So this one is pretty simple. It's a 3-to-3 ratio. You could also think about that. You could reduce it to a 1-to-1 if you wanted. So then the math here is actually really simple because you're going to multiply by 3 and then divide by 3. So our answer is still going to be 1.75, but now it's going to be moles of copper.